Okay, maybe we can start. Welcome everybody to this webinar, Athena webinar meeting for November. So let me introduce our speaker today, which is Paul Scholz. He did his PhD in McGill in 2017, then got a Covington postdoctoral fellow at the Radio Astronomical Observatory in Canada for 3 years, more or less, and then a Dunlap postdoctoral fellow at the University of Toronto till a couple of years ago, until she got assistant professorship in the Department of Physics and Astronomy at York University in Toronto, where he is now, and has, well, as you can see from the title, and most of you probably know him, he works on FRBs, especially with CHIME, with the new out triggers, and possibly with and definitely with cord very soon. And he's also very involved since more than a decade in trying to find the X-ray emission from these very interesting flashes. So I will leave now to Paul. I will give you 5 minutes if needed, or otherwise just only if you go very, very long. Otherwise, I would just keep you going as much as possible. So go ahead. Floor is yours. Paul, do you listen to me? Can you hear me? Okay. It won't allow you to unmute. Let's see if I can do so. No. Maite, can you unmute Paul?
Are you not?
There we go. Thank you.
Good.
Working.
Yeah.
Perfect.
Fantastic. Go ahead.
Always good to start with a little technical difficulties. Okay, thanks, Nanda, for the great introduction. And yeah, I'm going to talk to you about the search for X-ray emission from FRBs. And like Nanda said, I primarily have been working with CHIME over the past, well, not quite decade, I guess, but been working on FRBs for the past decade. And I'll, talk about kind of the current status of FRBs, which involves CHIME, and the future, which for X-ray, searching for X-ray emission should hopefully involve Athena and many more radio telescopes in the time between now and when Athena launches. There'll be many more FRB detectors coming online. So that will be important for the future prospects part of this talk. Yeah. So let's get started with what is a fast radio burst? Just in case you you're not aware, so fast radio bursts are bursts of radio waves first discovered in 2007. And what made them super interesting is that they were very short duration. When they were first discovered at a time span of about a millisecond, and since we've found them down to nanosecond durations. What made them more exciting than the pulses of radio emission that we get from within our galaxy, like from pulsars, is that these have a very large dispersion measure. And so as radio waves propagate through the interstellar and, well, for FRBs, the intergalactic medium, the the plasma in the ISM and IGM delay the signal as a function of frequency. The light, gets dispersed. And that's proportional to the amount of electrons between us and the source. And so when they were discovered, the DMs were very high. And so that said, okay, these look like they're extragalactic. And since then, we've localized many FRBs to their host galaxies. And so we've confirmed that they're extragalactic. given their distances inferred from their DMs, and for a few of them for the ones that have been localized to their galaxies where we measure their redshifts, they must be quite intrinsically energetic for short radio bursts, something like 10 to the 37 to 10 to the 42 ergs. And we've been saying, their origin unknown for quite a while now, I guess, well, since they were first discovered. We've got a lot of hints along the past 15 years or so, but still, I'd say the origin is not confirmed. It's still unknown. And so here's a slide here from the early days of FRB astronomy, from Jason Hessel's, where he shows that there are a lot of theories for FRBs, and a lot of these theories could still be valid. In the early days, there were many theories that said maybe they're galactic and the excess dispersion measure comes from something local to the source or near the source. But most theories are extragalactic, and most of them involve neutron stars or black holes, and that's primarily because of the duration, right? And there was a time when we would say the number of theories is more than the number of FRBs, because there's something like 100 theories, and we had only detected dozens of FRBs. Though these days, as you'll see, that's no longer true. And so, zooming a little bit on the possible models, the short duration and extreme energetics say that this needs to be coming from something where we're accelerating particles to relativistic speeds in order to create the coherent emissions. So you need extremely high magnetic fields or relativistic shocks. And so some of the theories here that are kind of leading these days are magnetars, as are a big popular theory for good reason. They have the highest magnetic fields in nature, of course, and or shocks, particles accelerated in shocks in the jets of accreting sources, shown in this model here. And then some sources are repeatable and some are cataclysmic. So you can destroy the source of your emission, and that would be cataclysmic. So for example, if an FRB could be produced in a neutron star, a double neutron star merger, that could only happen once. Another theory for fast radio bursts is the collapse of a neutron star into a black hole. If it is massive enough to no longer resist the neutron degeneracy pressure. All right, and so a big hint came in 2015 that repeatable theories are valid, right, and are necessary to explain FRBs, because we discovered repeating FRBs or repeating bursts from the FRB source, FRB 2011-02A, which we discovered in the P alpha survey in 2013, and we followed it up in 2015 and found 10 more bursts. And so this said that you need a repeatable model for this source. And so we know that at least some FRB sources can repeat. And as we've gone into the CHIME era where we're discovering a lot of fast radio burst sources, we found quite a few repeaters, something like around a few to 5% of the population has been observed to repeat. And so that lays the groundwork of what FRBs are. They are short bursts of radio waves, and the sources can repeat, although we don't know whether all sources need to repeat its possible cataclysmic events can explain, or can be a source for some of the population. But these days, what do we use to discover fast radio bursts? So CHIME is the big one, discovers FRBs at quite a high rate, several per day. Others, interferometers, DSA 110, ASCAP, and Meerkat are starting to get fairly appreciable FRB detection rates. And importantly, because they're interferometers with their elements spread apart, right? They can localize to something like arcsecond precision, where CHIME on its own we're performing interferometry just along these 100-meter focal line in between cylinders, and so our localization precision just with the CHIME core alone is much poorer than these other ones. And so a little bit more about CHIME, since it's my takes a lot of my day job, I guess. So CHIME is the Canadian Hydrogen Intensity Mapping Experiment, originally built to map hydrogen intensity to probe baryon acoustic oscillations, the signal from baryon acoustic oscillations in 21 centimeter, redshifted 21 centimeter. And so in order to, perform this, rapid mapping of the sky, what CHIME is it's 400-meter long cylinders, 20 meters across. And so because they are cylinders, they have a field of view which stretches horizon to horizon instead of, a small disk on the sky or like a traditional single dish telescope. CHIME is not just a telescope, it is also a collaboration of many people. Here's a subset of us that were able to get together in a face-to-face meeting in January 2005 at McGill. And so CHIME, because it is a cylinder, it consists of 4 cylinders. It forms a beam that stretches from horizon to horizon. So a single feed on a single cylinder would have a beam on the sky that looks something like this. Its width here is exaggerated. It's the width of the field of view is actually only about a couple degrees, and so I think in this illustration this spans more than a couple degrees. And then what we do is we take all the elements along each of the cylinders, all of the feeds interferometrically combine their signals and form 1024 beams on the sky, which we search in real time for FRBs. We have to search in real time because the data rate is too high to save it and search it offline. And so this leads to quite a high FRB detection rate. So here's a histogram of the discoveries of FRBs before CHIME. And in the early days, it was primarily single dishes, detecting something like a few FRBs per year. And Parkes was leading the pack with that. Arecibo in 2012 detected the repeating, what eventually became the repeating FRB. And in 2016 to 2018, interferometers were starting to pick up and leading to higher detection rates in their larger field of view. And then of course CHIME comes along with its incredibly high large field of view. Although as I get later into the future, maybe we should refer to CHIME as having a modest field of view. And CHIME detects something like almost 1,000 FRBs per year, a few FRBs per day. And so in this large sample, we put out our first catalog in quite a few years, or a few years ago now in 2021, our first catalog of 536 FRBs from our first 18 months of operations. And then coming quite soon, we've got it written up and it should be in the wild soon, is our second FRB catalog that goes up to about almost to the end of 2023. And so there will be about 4,500 FRBs in that sample. And so yeah. Okay, so CHIME is our, discovery machine when it comes to FRBs. We detect thousands of FRBs per year. But one of the problems with following up and understanding the origins of FRBs with them is where are they coming from, right? So CHIME's field of view is in the real-time pipeline, we have a localization precision of something, about tens of arc minutes wide. And, you localize an FRB to many tens of arc minutes on the sky, you're going to have a lot of possible host galaxies. So really, to search for things, well, like X-ray counterparts or understanding the host environment, etc., you need to localize to at least the size of a galaxy, so sub-arc second precision. And for this repeating FRB discovered by CHIME, it was discovered by CHIME in 2018, and then the European VLBI network later, because it's a repeating source, followed it up, discovered repeating bursts, and was able to localize it to 2 milliarc second precision and pinpoint the exact location within the galaxy that it's at. So these VLBI-like baselines are powerful for telling us where the FRBs occur and giving us hints for their origin. And so the next evolution of CHIME is to, add VLBI localization capability to it so that we can combine CHIME's high detection rate with milliarc second precision localization. And so this is not just a plan. We've got 3 telescopes deployed, fully instrumented, and currently being commissioned. So one about 100 kilometers away in British Columbia, one at Hat Creek Radio Observatory in Northern California, and one at Green Bank in West Virginia. And so we're starting now to achieve localizations with these 3 baselines. So our first catalog that we've already, of localizations that we've already put out is just using that short baseline with the nearby outrigger station. And so that gives us a localization precision of, something the scale of arc seconds in one dimension, and the best localization precision we can achieve, in the other dimension, kind of perpendicular to the baseline, is something around an arc minute or just under an arc minute. And so we get these long, these stretched out ellipses. But for many of them, it's enough to identify host galaxies. And so there are 21 host galaxies published in that catalog. And so in the near future, in the timescale of a year or of, a couple of years, we should have large catalogs of FRBs detected by CHIME with sub-arc second localization precision. And another milestone with CHIME outriggers is we did publish our first full array localization. This was an exciting source that was discovered in March this year, where we had a burst that was incredibly bright, about the brightest FRB that FRB has detected, or CHIME FRB has detected on axis. And because it's quite bright, that meant that it's coming from very nearby. And so there's this nice big galaxy. I think it's about 30 megaparsecs away. And the CHIME localization with the precision of something like, tens of milliarc seconds, pinpointed it to the star-forming clump right here. And another thing exciting about this is that we announced to the world that, oh, we found this bright FRB. We've localized it to this galaxy, this nearby galaxy, and so a team at Harvard got JWST DDT time, and so we can combine these super precise milliarc second localizations with our state-of-the-art infrared telescopes which it's just beautiful data. Love looking at JWST. You can see individual little clumps of stars. And so you can see that it was localized to the outskirts of this galaxy. And here's the little clump that wasn't resolved in the previous image. But at the location, there is a near infrared source here. And so we're at with JWST sensitivity and the milliarc second precision together, you could start ruling out the presence of things like is there a globular cluster or a young cluster at that location? What type of star could be at that location, which is going to inform on the possible origins of FRBs. All right, so I hope I've convinced you the era of thousands of hundreds to thousands of highly precise localization is upon us. So right now, we've got a large sample of FRBs from CHIME and from interferometers like ASCAP and MeerKAT, DSA 110, and CHIME itself. We're getting to dozens, maybe 100 FRBs localized to host galaxies. But then, over the next few years, there's going to be a big step in the number of precise localizations of FRBs. All right. So let's talk now about X-ray limits on FRBs. And maybe that's spoiling that we haven't made a detection of a counterpart, an X-ray counterpart of FRBs yet. I guess if we had, it'd be a more exciting talk. But I will start with a detection of an X-ray counterpart from what you might call a galactic FRB or a galactic FRB analog, or I think as we called it in the paper, a fast radio burst-like burst, or something, a millisecond duration burst of radio, a radio burst from a galactic magnetar. So this was in April 2020. CHIME detected an extremely bright fast radio burst. By far the most the highest flux or the most fluent burst CHIME has detected from an astrophysical source. And so this burst happened far off axis from where CHIME was, from above the telescope where CHIME is always pointing, straight up. So it's about 20 degrees off axis. It was where the magnetar was, or the source was at the time. And so that's what led to this knotty structure in the spectrum you see here. And we were able to use this knotty structure to localize it to the position of a magnetar that was known to be an outburst, SGR 1935 plus 2154. And although this burst was a lot less luminous than fast radio bursts that are coming from FRBs at redshifts greater than 1, right? It was still comparable to the faintest, the least luminous FRBs in the FRB population. And if you had taken this and put it in a nearby galaxy like Andromeda, it would have been detectable. So this says, probably some FRBs are magnetars. You could imagine just cranking up whatever's happened in SGR 1935 plus 2154 in April 2020. Just crank it up by an order of magnitude or 2, and it could easily explain the low luminosity end of the FRB population. But an open question is, are all FRBs magnetars? And a problem there is, well, can you crank it up to explain the energetics to explain the entire FRB population? You'd have to crank that up by about a factor of 1 billion. And also there's, as we'll get to, there are some FRBs localized to places where you wouldn't expect to find a magnetar. All right, so SGR 1935, we detected this FRB, and many X-ray telescopes, which were either all-sky monitors or paying attention to the source because it was an outburst, detected an X-ray burst at the time of the radio burst. So you see the radio burst in orange here, which is from CHIME, as it was detected with CHIME, and then you see in the integral data here an X-ray counterpart. And so we have a sample of one X-ray counterpart to FRB, or a FRB-like event, galactic analog to an FRB. And so that gives us a handle on possible X-ray to radio efficiencies that we might expect in the FRB population, because it's the only detection we do have. And so we can put that in context with other limits placed on extragalactic FRB emission, as well as what goes on, what magnetars and other galactic sources do in the X-ray. And so the line here is the energy emitted by SGR 1935 plus 2154 in soft X-rays, and at that for that April 20th event. And then here I'm showing the energy put out by magnetar short X-ray burst, intermediate flares, and galactic magnetars. And so some of the limits we placed these days, and I haven't yet put our best limit on here because that's to come, is they've all been placed using our most sensitive X-ray telescopes, Chandra, XMM, and NICER. And then the other thing that influences the depth that you can probe is, well, the distance to the source. If we have a nearby source, then we can place deeper limits in energetics, obviously. And so, to make progress on this, we need closer sources and bigger X-ray telescopes. And so, here at current sensitivities, XMM-like sensitivities are the distances that if we detected an FRB at 1 megaparsec, we'd be able to probe energetics down to just the tip of the starting to get into the magnetar short burst regime, etc. All right, so our best limit on the X-ray emission from FRBs comes from this source that was localized to the outskirts of M81, which is at a distance of about 3.6 megaparsecs, and CHIME localized it here, off the edge of the M81 disk, and then later the European VLBI network detected repeat bursts from the repeating source and localized it to milliarc second precision to a globular cluster that is, orbiting M81. And so this globular cluster is a red dead population of stars, not a place you'd expect to find an active magnetar that formed in a recent core collapse supernova, right? And so this is kind of one of the points against the magnetars explaining all FRBs. Of course, you could form a magnetar through alternative mechanisms like accretion-induced collapse or in mergers, maybe. But it's it's unclear what kind of rates of magnetar formation you could get in those channels. Well, I shouldn't say it's unclear. There are papers written on it, so there's some clarity, but the rates of magnetar formation are much lower than the core collapse channel. And so what we did is we did both joint observations with XMM and Effelsberg to detect radio bursts during our X-ray observations. And we did some nicer observations coordinated with Effelsberg and during CHIME transits. And we were able to place the deepest limit with nicer. And again, this is, it's, just getting to the edge of magnetar short bursts, and it's still about an order of magnitude above the energetics of what was seen in the SGR 1935 galactic FRB analog. And on this plot, I've also added type 1, we've also added type 1 X-ray bursts to show how it probes into accretion-powered bursts as well. And so you see there's still a lot of fainter X-ray activity to probe, both from magnetars and accreting sources. We also were able to place limits on persistent X-rays, so a flux limit over during for the whole duration of the observation, not just as at the time of radio bursts. And so these, the deepest ones are from Chandra and XMM. So these are starting to, get, they rule out, for example, an ultraluminous X-ray source at the location of, or in the globular cluster, right? Which maybe, isn't too surprising since ULXs are kind of defined as having a high luminosity, but we're just starting there. We can rule out, the brightest LMXBs, HMXBs, and we're still orders of magnitude above detecting the persistent emission from a magnetar. And we would be sensitive to something like the Crab Nebula there if, for some reason there was a crab-like source in a globular cluster, not that you'd expect to see one there. All right, let's see. So complementary direction to go with, or another strategy to go to probe for FRB, X-ray counterparts to FRBs, is instead of going after nearby sources where you're going as basically as low as you can go in energy of X-rays, is to say, okay, if our sources all have similar efficiencies between X-ray and radio, if we get a bright FRB, it should have a bright X-ray counterpart. That makes sense. And that is, to some extent, that is independent of distance, right? Although, if you detect a bright radio burst, statistically, it's likely to come from more nearby. But given that we don't know the origin of FRBs, maybe it's possible that there are rare, extremely bright FRBs that could come from gigaparsecs away and give us an X-ray counterpart. And so these, on this plot, I've plotted the X-ray to radio ratio, and then over some different bands in the X-ray and soft gamma rays that these limits have been placed. And you can see we're still a couple orders of magnitude above the efficiency seen in SGR 1935. And so if I want to, kind of forecast here with XMM, nicer Chandra-like sensitivity, we would need something like Kilojansky millisecond fluence burst in order to detect, to get close to SGR 1935 like efficiencies, right? And so for those of you who don't know radio FRB fluence units, that's a very bright burst, an extremely bright burst. And so along these lines, we've tried to, the best way, one strategy to get a super bright burst is to go after a very hyperactive source. And if that source, is drawing from a large distribution of energy, hopefully it has a rare one that's extremely bright. And so what we did is we took this source, FRB 2022-0912A, which for a few months in 2022 and 2023 was giving us a few FRBs per day. On some days, more than 10 we were detecting per day. And so we coordinated XMM, Newton, and Effelsberg and nicer observations with CHIME pulsar. And during our X-ray observations, we detected quite a few radio bursts. And so at the times of all of those radio bursts, we can say, okay, what X-ray could be there? And then we statistically stack those limits together to achieve, kind of our deepest limit on an extragalactic FRB source. And you can see we're starting to get close to SGR 1935, like X-ray to radio efficiencies ratio. All right, so that's kind of our current status of X-ray emission or X-ray limits on X-ray emission from FRB radio sources. And you can see, we've still got a ways to go. Especially if we're trying to, find something like if the counterpart is something like what a magnetar, a run-of-the-mill burst from a magnetar, for example. But the future is looking bright because of two things. One is that we're going to get better at discovering fast radio burst sources. So these are some future fast radio burst surveys. CHORD, the one I'm involved in, and which is currently under construction at DRAO. So here's a recent dish photo of us, of the dishes we're deploying on site. And then some other surveys, the Deep Synoptic Array 2000 in Nevada. SK, of course, will be, with its high sensitivity, will be fairly good at detecting especially very distant FRBs. And then in the complementary direction is something called Burst, being built in Taiwan, which is dipole arrays with extremely large fields of view, but much less sensitivity than CHIME or CHORD or DSA. And so I'll talk a little bit about CHORD because it's another one that I work on. So CHORD is going to consist of 512 6-meter dishes next to CHIME. And so these 512 6-meter dishes are going to give us much more collecting area than we have CHIME, allow us to discover more FRBs. Another thing is that it's probing a wider band, so from 300 to 1500 megahertz instead of 400 to 800 megahertz of CHIME. And so we should discover more FRBs because we're probing a wider band. And so the expected discovery rate of FRBs for CHORD is something like 10 to 20 times that of CHIME. And we'll also have outrigger stations just like CHIME in order to provide that VLBI level localization precision for all the FRBs we discover. All right, and here's a slide has a bit more on the detection rates, and so you can see, our current FRB machines are, kind of here. We've got Chime turning into a powerful localizer with Chime outriggers. ASCAP, Meerkat, DSA 110 have pretty good localization precision. And then DSA 2000 and Chord are going to, push that discovery rate up quite a bit. And the strategy here is more collecting area to detect fainter and more distant FRBs, and Chord will have quite good localization precision because of its outriggers. But a complementary direction, especially when it comes to detecting counterparts to FRBs, is to try to detect primarily nearby FRBs. And so there's a few FRB detectors doing that, going after this. There's the burst array in Taiwan, and this plot is from the burst overview paper, which shows that they're going for large field of view, right? So 10,000 square degrees, and with an FRB discovery rate that's something like, in their initial iteration, less than 1 FRB per day, but as they grow the array to if they build the larger version of their array to several FRBs per day, and so that'll be a Chime-like FRB discovery rate, and then that's in contrast to DSA Chord down here, much smaller fields of view, higher FRB discovery rates, but those FRBs are going to be at a much larger distance than what are discovered by these large field of view detectors. So there's an animation here which kind of shows this from Liam Connor at Harvard, who's involved in building this coherent all-sky monitor, which has a similar strategy to burst. And you can see, though, the traditional FRB telescopes discover many more FRBs in the local universe, so within about 100 megaparsecs, it's much more efficient at discovering these bright nearby FRBs because of the huge field of view. And then a third one of these is the Canadian-Chilean Array for Radio Transient Studies. Hopefully I got that right. CHARTS, which is being built in Chile with a similar strategy, having, a wide field of view, feeds pointed straight up at the sky in order to detect bright FRBs over a wide field of view. And so where does this leave us in, when we have Athena, right? Or NewAthena. So we should have large samples of FRBs, maybe something like hundreds of thousands of FRBs, maybe many hundreds into thousands of local universe FRBs within something like 100 megaparsecs. So I'm thinking that, in a decade from now, we will have no shortage of targets to look for to characterize X-ray emission. And whether or not we will be characterizing known X-ray or characterizing emission from known X-ray counterparts to FRBs, or whether we will still be searching for those counterparts to make that first detection, obviously, I don't know. It depends on what their counterparts are, of course. But at any rate, Athena will be a huge step forward in, X-ray sensitivity, as I think this audience probably knows. A factor of 10, about effective area in compared to XMM, right? And so we'll be, if we'll be able to hopefully probe X-ray emission and along with FRBs in whatever is causing fast radio burst, right? We could be observing accreting sources where we see the X-ray emission from accretion and then fast radio bursts from the coherent emission in shocks in the jets. We could have maybe something like a magnetar where FRBs are produced in the magnetosphere and we're probing thermal X-rays on the surface of the magnetar. You know, what phenomenon the X-ray emission would probe depends on what the FRB sources, you know, are, of course. And so what does this look like in, you know, kind of some of the plots I showed before if I switch from Chandra-like or Chandra and XMM-like sensitivity to NewAthena? And you see that for the very nearest galaxies, we'll be able to probe into to SGR 1935 X-ray counterpart, FRB X-ray counterpart energetics, the bright FRBs that we would need to detect in order to probe down in X-ray efficiency are a bit more modest into the hundreds of Jansky milliseconds. And so there, you know, we're going to, you know, if you have X-ray counterparts that are, you know, comparable to the bright end of galactic X-ray sources, both accretion powered and magnetars, you know, they would easily be detectable in nearby galaxies. And just to put, you know, this 100 Jansky milliseconds in context, hyperactive FRBs actually, you know, they do put out fast radio bursts that bright. This is a plot from that source that we placed limits on FRB 2022-09 something something. 0911 maybe. Oh, I should have written on this slide. But at any rate, that hyperactive FRB source was observed with many radio telescopes. You know, many thousands of bursts were detected by FAST. You know, with its 500-meter dish is a very prodigious detector of repeat bursts from FRB sources. But then also with small dishes, Westerbork and the Stockert telescope and Nancy, they saw, and it's been seen in several repeating FRB sources now, kind of a plateau or maybe a foot to the FRB SED, right? And so there are these bright bursts that these sources put out that could, you know, reach these hundreds to thousands of certainly hundreds of Jansky milliseconds. And so with a, you know, more wide field FRB detectors where you can catch these rare bursts and a powerful X-ray telescope, you know, probing deeply in efficiency here should be quite possible. And then another direction is persistent emissions of X-rays. So I said that our current limits with XMM and Chandra, you know, are still an order of magnitude above what you'd expect from magnetars. So magnetars in outburst have kind of a max persistent luminosity of 10 to the 36 ergs per second. And if my back of the envelope calculation is correct, in 100 kilosecond exposure, you could detect these magnetars in outburst out to something like 10 megaparsecs. And so if fast radio burst counterparts or the source of fast radio bursts are magnetars, and we have them and we have some FRBs in the, you know, within 10 megaparsecs, which we hopefully should have many sources in, you know, in a decade from now, we'll be able to detect and characterize their persistent emission. All right, so thank you for listening. To summarize very briefly, the takeaway message is, I guess, we're currently limited by our ability to probe for X-ray counterparts by, our current fleet of X-ray telescopes and a low number of nearby and bright sources to observe. But over the next decade, both of those should improve, substantially with, NewAthena providing this step in X-ray sensitivity and future FRB surveys giving us more promising sources for detecting these counterparts.
Thank you very much. Thanks a lot. Extremely interesting. Very nice talk. And maybe I'll open the floor for questions. I have a few, but I will ask Maite to open the mic. Can you open the mic for Martin?
We have also the question and Q&A questions, right? You can see there, I guess.
Yes. I will read them later.
Okay.
Yes. Or maybe if
I
they
open
want
Martin.
to ask the question themselves, I will select.
So Martin,
yes,
you are allowed to talk.
Okay, thank you. Hi, Paul. Thanks for a very nice talk. Sorry, I didn't see the Q&A section. So I wanted to ask, like, when you talk about the X-ray counterpart to radio FRB or the FRB counterpart to X-ray source, do you mean any counterpart, or you mean just some time coincidence as well, like looking within the certain, like a time window where you expect like a simultaneous emission, and what would be the window? That's just must it happen like simultaneously or not? Or sometimes you see just the radio, sometimes you see the X-ray, or rarely both. Or
yeah. So I mean, right now we don't see anything, right? We haven't made any detections of the X-rays, but we're looking for any X-ray emission from the source of FRBs. So looking at the time of radio bursts basically just reduces your trials factor so you can probe, deepest. And we also, play games like widening the window that you look for counterparts away from the FRB. Of course, if we have a 10 kilosecond or 10 kiloseconds of X-ray data, we're going to search the whole thing for FRBs, but your limit away from just the time of for an X-ray counterpart, but your limit just at the time of the FRB is going to be deeper because it's kind of where to look. So yeah, we're not just limiting ourselves to the time. It's just when I plot our best limits on the prompt X-ray emission, that is just placed at the time of the FRB because that's where you can go deepest.
And sorry, so you don't have any like a expected time window where to expect one or the other? I understand that your strategy is to first start with the feasible, and then even this one is like any counterpart is difficult. But if you would imagine that you have like a much worse localization, so if you have too many sources, they will sooner or later cross over on the sky, but not within the time. So if you have a guess, what would be your guess?
Yeah, so the different models predict different delays between radio and X-ray, and a lot of them are in the time scales of like milliseconds to seconds, and of course SGR 1935, we have an example of a FRB-like one where they line up and they're consistent within about I think there's the radio led the X-ray peaks by about 6 milliseconds, I think was the result there. But that's, of course, is one source that tells us the possible delay between the two. Yeah.
Okay, let me go to the other few questions. Let me read the first one. Is there a place where FRB detections are distributed in real time? where people can have it in real time and follow it up?
Yes, so Chime has a VO.
Animatica.
Yeah, Chime has a VO event service that you can subscribe to, and our FRB detections are, sent out in real time. Don't have a link for it handy, but if you go to chime-frb.ca, I believe there should be information there about the VO event service.
Okay, thanks. I'll read another one. Remember that if you want to speak, you can do it. Just raise your hand. Next question is by Rana Starling. Thanks for the interesting talk. Is the SGR plot radio and X-ray light curves overlaid? There appeared to be a time lag between the two. Can you comment on this? Well, yes, I think you just...
Yeah, so I guess I did, but we can go back and look at it briefly so everyone has the context. Yeah, so yeah, it looks like there's, a bit of a time lag here. And we wrote a paper where we were very careful in trying to characterize the time of arrival of the FRB and taking into account all the systematics. And I think the conclusion there that it was, consistent with about the 6 millisecond lead of the X-ray or radio to the X-ray here. Although, after taking into account systematics, the error bar on that 6 is a bit larger. Yeah. So that was, I guess I don't have that cited here, but Geary et al. I don't remember the year now, but maybe 2023 or 2024.
Okay, thank you. Another question by Stephen. Is there any connection between FRBs and fast X-ray transients?
I have to say I'm not super familiar with fast X-ray transients. My understanding is that they are on, their definition of fast, or the definition of fast there is quite different than, millisecond. So, the time scales there aren't quite compatible, but given that we don't know what FRBs are, maybe.
Okay, thanks. There is another question by Luigi Piro saying, I fully agree with your assessment on the capability of NewAthena on the FRBs, and we have achieved similar assessment. On the persistent radio sources, one caveat we should look at is the contamination by star formation X-rays. In fact, in one FRB, we had a marginal Chandra detection that we attributed to star formation.
Yeah, this is another issue, with Athena's PSF is that there's going to be a non-negligible chance coincidence, chance that you get star formation there. Or I did mention this source here. This one here. So when we first localized this, there was an Einstein probe detection of an X-ray source in, a region about this size. And Chandra later localized the source to within just an X-ray source within just a few arc seconds of this fast radio burst. And so if you did take, an Athena like PSF, those sources would be coincident, right? I think. Well, I guess it depends on how many arc seconds exactly and how well you can centroid, but and so there is a non-negligible probability of a chance coincidence. So there, it's going to depend on characterizing the source and certainly if both sources show variability at the same time, then your confidence that it's a real association would go up.
Thank you. Remember that you can raise your hand and pose your question yourself. There is another question which is anonymous. I don't have the name here. Is there any direct correspondence between repeating FRBs and magnetar X-ray tied to rotation of the magnetar? I assume that it means whether you find hints for rotation, for example, in the repeating ones.
Yeah, whether there's any periodicity in repeating
Yeah.
FRBs that could be explained by the rotation of a magnetar. No, we haven't seen any periodicity on the time scales of seconds or minutes. Magnetar periods, I guess, are getting longer, have gotten longer over the past decade or. But yeah, the only periodicity seen in a repeating fast radio burst source or sources have been seen on the time scale of days. So there's one with the 16-day periodicity and another one with 167, I think, day periodicity. And so those would be, more of a maybe orbital time scale or something like that. Yeah.
Yeah. Yeah.
Maybe precession. I think precession of a magnetar is one of the models to explain it, but yeah, no smoking gun for sure.
Okay, thank you. We have another question by Domitila de Martino. What observing strategies foreseen for NewAthena to catch X-ray counterpart? So this is.
Yeah, so I mean, I think that really depends on where FRB astronomy is in a decade. If we, have made detections of X-ray sources or X-ray counterparts of X-ray, sorry, X-ray counterparts of fast radio bursts, if we've made those detections, I think Athena will be, extremely powerful in characterizing those sources, right? We might make a detection that's marginal and it's claimed. Maybe we see some variability that that gives us confidence that the association is real, but we might not be able to characterize the source in much detail until we get Athena-like sensitivity. And of course, having the other direction is if we haven't yet made an X-ray counterpart detection, and then in that case, I think you would want to prioritize the sources that you go out after to be the most nearby, and maybe if we have some nice nearby hyperactive sources that are known to emit bright fast radio bursts, those would be the best targets to go after as soon as Athena's good to go, right?
Yeah. I saw Carlo. Do you want to say something, to add something about this?
No, in reality, no. I haven't raised that.
Sorry. I saw you were talk permitted, so I don't know, maybe my
No, it was.
Okay, that's fine. Okay, good. So we have one last question by Chiro. I recall you that you can raise your hand and pose your question yourself. Yes, thank you, Chiro. Maite, can you? Thanks. You can.
Can you hear me?
Yes, perfectly.
Okay, thanks. Great talk. I was wondering if you adopted the peak of the X-ray luminosity to kind of estimate the detection, or you assume a general overage flux.
Sorry, I guess I don't understand. So did you?
Yeah, maybe I can explain. In the case of the magnetar, you had this kind of detection in the X-rays with a peak of the light curve. In order to estimate the detection of other FRB or even with Athena, the 10 to the 36 per second comes from the X-ray peak or comes from an overage luminosity?
You're saying so for my forecasting, yeah. So I guess for the 10 to the 36, that is like the highest persistent meaning, lasting on the time scale of an observation, say maybe over the time scale of a day. And that's that 10 to the 36 is kind of a limit that's I'm trying to find the slide, but will I get to it? Yeah, here we are. Yeah, that 10 to the 36 is a limit that's thought to be, you know, kind of physical. It's the hottest, you know, you can heat up a neutron star before neutrino cooling starts to dominate. And so, but that 10 to the 36 is like the brightest persistent luminosity you can get. Of course, magnetars put out the short X-ray bursts and giant flares and stuff that can get much brighter. And so those much brighter, like peak fluxes are what are used in my, you know, kind of forecasting here, right? For the bursts.
Okay. Okay. And could you, I don't know if we still have time, but could you clarify? Okay, could you clarify to me why ULXs are considered feasible counterpart? Because they are generally young objects with strong accretion rates, so not necessarily accreting magnetars, but at least if we assume a dipole configuration, not a quadrupole.
Sorry, were you asking about the accreting sources?
Yeah, ultraluminous X-ray sources. How come they are considered possible origins of fast radio bursts?
So the thought there is that in the jets of the accreting sources, you have you know, accelerated particles getting shocked, right? And then in the shocks, they produce coherent radio emission. So it's not, yeah, it's that relativistic flow coming out from the, you know, in the jet.
Okay, so like microquasars, basically. Okay.
Yeah.
Well, thank you. Thank you.
All right, I'm noticing that it's past 10 a.m. and I do have a meeting at 10 a.m. Sorry, maybe I should
Yeah, that's fine. So
notified ahead of time.
thank you.
Yeah.
That's okay. Actually, we don't have the question. I had a couple, but that's absolutely fine. So thank you very much for your wonderful talk, and we really hope to see an X-ray counterpart very soon, hopefully even before Athena, because that will be fantastic. So I thank you again, and thanks everybody for attending, and see you.
Thanks everyone for listening. Your interest.
Thank you.
Okay. Just a last reminder that our next webinar will be on November 13th by Martin Meyer, talking about supernovae remnants with E. Rosita. See you there.